So we'll start unit number 5, synthesis of mechanism. So before start of this unit, as already we discussed some analysis part in theory of machine. So I want to ask you what basic difference you know between synthesis and analysis. Yes, please. What is difference between synthesis and analysis? In Tom 1, we studied analysis of motion, like velocity acceleration analysis. Now we are learning synthesis. So what basic difference is there between synthesis and analysis? Yes, anyone please? Means what is expected to do in synthesis? Am I audible? Hello?
Yes, sir, you're audible.
Please reply. Okay. So don't know what is synthesis? No one knows what is synthesis? Okay, so let's start what synthesis is and what you are going to do it in this unit now. Basically, a synthesis is, we know that synthesis means, let's say talk about synthesis of mechanism. Synthesis of mechanism is design or a creation of mechanism to produce desired output motion for a given input motion. Means if certain input is known to you, and for that input you want some desired output motion, then finalizing mechanism, designing mechanism or creating mechanism to give that output, that is to give that desired output for a given input, is nothing but a synthesis. In other words, we can say synthesis of mechanism deals with determination of proportions of mechanism for a given input and output motion. So in simple word, we can say synthesis means we are going to design a mechanism, we are going to create a mechanism, but for what? To obtain a desired output for a given input motion. When we talk about example of this, we seen some numericals on cam and follower. In that case, displacement diagram is given to you or follower motion is given to you, means input is known to you, which kind of follower, which type of follower motion, that is known to you, and for that follower motion, for that input, we are supposed to draw a cam profile. So that process to design a cam profile is nothing but a synthesis. Is nothing but a synthesis. So example of synthesis is nothing but a designing a cam to give a follower a known motion from the displacement diagram. In another example, you can take like determination of number of teeth on the members in a gear train to produce a desired velocity ratio. So to obtain a desired velocity ratio, we are going to find out number of teeth in case of a gear train. That is also one type of synthesis we discuss. So synthesis problem already we discussed in a gear train topic or in a cam and follower. So I hope you understand what synthesis is. I repeat again, it is nothing but a design of mechanism or finalizing dimensions of mechanism, or you can say creating a mechanism, but for what? To obtain a desired output for a given input motion. Means if input is known to me, what output I have to obtain, that is also known to me. So that process, in that case, the creating or designing a mechanism is nothing but a synthesis. Is it clear? Hello? Are you getting or not what synthesis is?
Yes, sir.
Okay. Please reply. I request again and again so that I understand whether you are getting or not. Okay. So I just discussed definition of synthesis with you. Remember, in this lecture particularly, we are going to discuss theoretical topic of this unit. What theory required for solving numericals, for solving derivations. That topic we are going to discuss in this unit. In next lecture, we start with derivations and numericals. So theory portion we are discussing. I just discussed with you what is definition of synthesis. Now there are some steps in synthesis. Basically, in the application of synthesis to the design of mechanism, the problem of synthesis divides into 3 steps, or you can say 3 parts. That is, type synthesis is the first step, number synthesis, and dimensional synthesis. So there are 3 steps in synthesis: type synthesis, number synthesis, dimensional synthesis. Now we'll see this one by one. So what basically type synthesis is? Type synthesis is first step in synthesis process, in which, remember, at the end of this 3 steps, our mechanism is finalized, our design is finalized based on desired output for a given input. So what first step is, in type synthesis, we are going to select, or we are going to select a mechanism. Which type of mechanism we need to use for that output, for a given input. So here the type synthesis basically refers with a selection of mechanism. So in type synthesis, we are going to select a mechanism. So first step is nothing but selection of mechanism. So type synthesis refers to a selection of mechanism. Now different mechanisms are there. Based on requirements, we are going to select that particular mechanism. Example, you can select a linkages, or you can select a gears, or cam follower. Means there are different options like linkages, gears, cam follower, belt and pulleys, or you can say chain drives or a sprocket, like this. Means there are different options. So first step is to select mechanism for according to requirement, and the selection of mechanism nothing but a type synthesis. We can also note that during selection of mechanism, one may have to consider design aspects like manufacturing process, material selection, space consideration, and safety consideration. Means along with selection of mechanism, we need to also consider these 4 aspects, like a manufacturing process, what kind of manufacturing process we are going to select, we are going to use for manufacturing that mechanism, what kind of material we are going to use for that different parts manufacturing, then how much space required to fit that mechanism, and also along with this, we need to consider safety consideration also. So that also involves in a type synthesis. So I think I explain you what is first step in synthesis. That is nothing but a type synthesis. It refers to a selection of mechanism, type of mechanism we have to select. At the same time, we need to consider manufacturing process, material selection, space consideration, as well as safety part also we need to consider. This is first step in synthesis. That is nothing but a type synthesis. A theory question can be asked on this topics that we are going to discuss in this lecture. So prepare this topic properly, listen it carefully, try to understand. Second step in synthesis is number synthesis. So after type synthesis, next one is number. In number synthesis, we can say number synthesis refers to a number of links in a mechanism, number of joints in a mechanism, or means we are going to select how many number of links will be there. In the first step, we select mechanism. Let's say we talk about a 4-bar mechanism. In that case, only there are 4 links, but how many joints are there? Which type of joints are there? Also, it includes a degree of freedom calculation, a degree of freedom required for specific motion. So in number synthesis, we are going to finalize number of links, number of joints, number of pairs, and how many number of degree of freedom required to obtain a specific motion. So that is what number synthesis is after a type synthesis. Means in the first step, we select a mechanism. Let's say we talk about linkages. We select, let's say, 4-bar linkage. In that case, after selection of 4-bar linkage, in second step, that is in number synthesis, we are going to select how many links. As it is 4-bar, we know 4 links are there. But which types of links are there? Then how many joints will be there? Which type of joints will be there? And then number of pairs, then degree of freedom. If you know number of links, joints, pairs, then you can calculate degree of freedom of that mechanism. So all these calculations involve comes under a category of number synthesis. So second step is types. First step is type synthesis, and second step is number synthesis. And the last step, that is third step, which is very important, is nothing but a dimensional synthesis. In dimensional synthesis, you can see dimensional synthesis refers to find out dimensions of mechanism. Means in the first step, we define which type of mechanism. In second step, we define number of links, number of pairs, number of joints, its degree of freedom. And in the last step, that is in dimensional synthesis, we are going to select its dimensions. Finally, we are going to select, suppose there are 4 links, but how much length of each link is? What is L1, L2, L3, L4? How much theta 1, theta 2, theta 3, theta 4? Likewise, you can say the length of the links, then you can say angle between the different links, or we can say a distance between pivot points, angle between the arms, links. Then in case of cam profile, we are going to select how much how the cam profile is, diameter of roller follower, gear ratio. So all parameters related to dimensions we are going to sell it in a dimensional synthesis. And this is your last step in a synthesis process. So we've seen 3 steps in synthesis process. One is type synthesis, second one is number synthesis, and third one is dimensional synthesis. Is it clear? Hello?
Yes, sir.
Okay. Type, number, and dimensional. These are the steps in synthesis process. Now, after discussing steps in synthesis process, next step is, or next topic is tasks of kinematic synthesis. Which are the tasks of kinematic synthesis that we are going to discuss now? Remember, task may be sometimes also called the classification of synthesis problem. Means it can be asked like this: classify synthesis problem, or explain classification of synthesis problem. So it is same with nothing but a tasks of kinematic synthesis. In task, generally a synthesis problem is classified into 3 types. That 3 types are function generation problem, path generation problem, and body guidance. Body guidance sometimes also called as a motion generation. Remember, we are just preparing you for a designing of mechanism, and for designing of mechanism, creation of mechanism, we are studying now what theory required for that design. So first we discuss types. Now we are discussing task, or you can say classification of synthesis problem. So there are 3 types of synthesis problem. Means synthesis problem may be a function generation problem, it may be a path generation problem, or a motion generation problem. Motion generation can also be called as a body guidance. So there are 3 tasks of synthesis as discussed. Now we will discuss these 3 tasks one by one. The first one is function generation. Now what do you mean by function generation? Basically, let's say consider this mechanism, a 4-bar mechanism. In this 4-bar mechanism, there are 4 links, as we know, 1, 2, 3, 4. The second link is input link, 4th link is output link, 1 link is fixed, and link number 3 is a coupler. If we need a motion in such a way that output motion is function of input motion, means this output will rotate, oscillate, or reciprocate according to function of time or function of input link, then this problem is nothing but a function generation problem. Means output, we want this output, let's say y is output, motion of output link, but the y is function of x. Means output motion depends upon motion of input link. So this kind of synthesis is called as a function generation problem. Means we can say in designing a mechanism, the frequent requirement is that output link that we already discussed, let's say link number 4 here, output link should rotate, oscillate, or reciprocate. It may be any motion according to specific function of time or function of motion of input link. So that's what I discussed with you. If this output link, motion of output link is function of input link, then that synthesis problem is nothing but a function generation problem. Let's say y is equal to f of x, where y is motion of output link, and it is function of x, where x is motion of input link. It may be a displacement, it may be a angular displacement, linear or angular. So it may be a theta and phi, we can also call it as. So whenever output motion is function of input motion, then that synthesis problem comes under a category of a function generation. Example, you can say, just we can already discuss a simple example. A 4-bar mechanism is to generate the function y is equal to f of x. In this case, x represent motion of input link, as I discussed here, and the mechanism is to design so that motion of output link approximates function of y. Means if y is equal to f of x, where y is motion of output link and x is motion of input link, then this problem comes under a function generation problem. So in function generation problem, these are the things where the output motion is function of a input link. Y example, y is equal to f of x, where y is motion of output link and x is motion of a input link. Now let's just talk about some examples of function generation problems. This is one example. You go through this carefully. And you can see here function generation basically related with a links connected or fixed with a fixed link. Let's say 4 is connected to fixed link, 2 connected to fixed link. So 4th one is output motion and 2 is input motion, where output is function of input link. So we can see here a function generator is a linkage in which relative motion between the links connected to the ground is of interest. So we are interested in motion of the links which are fixed to the ground. Fixed to the ground means the links which are fixed to the fixed link. Here the fourth link, or you can say second link, is fixed to the ground or fixed to the fixed link. Hence, the motion of these two are of interest. Example is a 4-bar hand actuator wheelchair brake mechanism. In that case, we can see there are different links like 1, 2, 3, and 4. So we are interested in the link number, in the motion of the links which are connected to fixed link. So this motion of the wheelchair is nothing but a function of a is example of a function generation problem. So while designing this wheelchair, we are going to design in such a way that the output motion is function of a input motion. That is why, suppose y is output motion, then it will be function of a input motion, let's say x. Another example we can consider here, let's say this one is a 4-bar linkage for a lawn sprinkler. This one is sprinkler, you can see this one is sprinkler here, and the mechanism to obtain that sprinkler motion is discussed here. This one is input link and this one is output link. So with this output motion of the sprinkler is function of input link, and hence this problem comes under a function generation problem. I am just trying to explain you what is basically a function generation problem, in which output motion is function of a input motion. Keep in mind, we need to compare this function generation problem with other generation like path and motion generation. So function generation, I think clear. You can take a few more examples like this. In this case, we can see this one is a mechanism to operate artificial hand used for a gripping. So this is different. Let's say this is one position, second position, third position. So in different cases, the output y is function of input 1. And another example is here, a 4-bar function generation mechanism to lower attic stairway. So you can see different positions are discussed here, but of course the output motion is function of input 1. So all these are functions, or all these examples of a function generation problem. The second type of problem or classification of synthesis problem is path generation. So let's say again, see in the last case what we discussed is output motion or motion of the link 4 is function of input. But if we are not interested in output motion, which is function of input, but in path generation, the mechanism is required to guide a point. Keep this thing in mind. Mechanism is required to guide a point. Now, which point we are talking about? That may be a tracer point or a coupler point. Example you can see here. This one is input link, which rotates like here. This one is output link, and this link number 3 is a coupler, as well as this link is a fixed link. So this one is a coupler. Let's say triangle BEC represents link number 3, or called as a coupler link. But we are not interested in motion of this coupler link, but here in this case we are interested in motion of a point. So this point is considered here, let's say coupler point, or called as a tracing points. So whenever path generation means the mechanism is required to guide a point. So we are talking about in this case a point E, let's say. Guide a point, that point is a tracer point or a coupler point along a path having a prescribed shape. So we are interested in motion of this point, and this point will trace a path. But the path is a prescribed path, is fixed path, a specific path. So we need to guide this point along this path. Let's say consider this path y is equal to f of x. Remember here, even though the path y is function of x, but we are not interested in motion of output link. Here we are interested in motion of one point, which is on any link maybe. So in this case, the point is on a coupler link. It may be on output link also. So whenever we are interested in path of a point, path traced by point, which then that problem comes under a path generation. So I repeat, in a path generation, the mechanism is required to guide a point called the tracer point or a coupler point along a path having a prescribed shape. And the common requirements are that a portion of the path either be a circular arc, elliptical, or straight line, means different paths are possible. So whenever we are interested in path of a point, the tracer point or coupler point, then that problems of function generation, the problems of synthesis comes under a path generation. And the last one is function. So we also talk about example of this. Now see here. This one is example of a path generation problem. Actually, it is a crane, and it is desirable. Now here we are. Let's say it is link number 1, link number 2, This 3 is a coupler link. You can say this one is coupler link, and this one is fourth link. Here we are not interested in motion of the output link. If we are interested in motion of output link with respect to input link, then that problem comes under a function generation problem. But here we are not interested in motion of the output link, but we are interested in motion of this point, which is on a coupler link. That's why this problem comes under a path generation problem. We are not only interested in motion of that point, but we are interested in path traced by that point. So you can see here, this one is the path traced by that point, which we consider. So this problem of synthesis comes under a path generation problem. So in path generation, we are concerned only with a path of a tracer point and not with motion of a coupler link. It is also important here, we are interested only in path of this point, we are not interested in motion of that link on which that point is on which that point is there. So here this point P is on link 3, but we are not interested in motion of link 3, but we are interested only in path of this point P. So these kinds of problems comes under a path generation problems. So I talk about function generation, I talk about path generation, and next we'll discuss about a last type, that is a motion generation. So here in path generation, we are interested in motion of a point on any one link. But in motion generation, generally a body is guided, entire body is guided usually as a part of a coupler link. Means whenever we are interested in motion of a whole link, complete link, and particularly a coupler link, then that problems come is nothing but a motion generation problem. Problem means we are saying a synthesis problem. So it comes under a motion generation where body guidance means whole body is guided, entire body is guided in some subsequent steps. So in body guidance or motion generation, entire body is guided usually as a part of a coupler link. Example we can talk about. In a construction industry, heavy parts such as buckets or blades of bulldozer must be moved through a series of prescribed portions. So here we are interested in that construction industry, we are interested in motion of bucket. So bucket is a coupler link, let's say. Bucket is a one link. So we are interested in motion of that bucket or blades. So entire motion of that link is considered. Let's say that bucket is nothing but is coupler link 3 here. So we are interested in motion of this link, not motion of a point. Even though diagram is same here, but whenever we are interested in motion of the coupler link, entire link, then that problem comes under a motion generation or a body guidance. So that's what about 3 tasks of kinematic synthesis. First one is function generation, path generation, and motion generation. You can note that in path generation, one is concerned with path of a trace point, and the trace point is on a coupler link, but we are interested in a path of a trace point which is situated on a coupler link. But in case of a body guidance or in case of motion generation, the entire motion of coupler link is concerned. Means here, whenever we are interested in coupler link motion, that problem is a problem of a motion generation. But whenever we are interested in a motion of a point on a coupler link, path traced by a point on coupler link, then it comes under a path generation problem. So I think it is clear what is function, path, and motion generation is. We'll talk about example of this motion generation also. Now you can see here a 4-bar automobile hood linkage. This one is, this one is hood to operate the, which is in the one position it is shown here. This one is in this position. So whenever it is moving from its initial position to this position, this link 3 is important. So motion of this link number 3 is considered here. It's attached to that hood and it is moving through successive steps. So whenever you are interested in motion of the coupler link, that problem comes under a motion generation problem. Now some students might be worried about what sir is talking about, what path, what function, what motion is. Remember, this is synthesis part, analysis synthesis part, which is required for design of mechanism. So in that case, we must know, means suppose any problem is given to you, then you should classify that problem into 3 types. Either it is function, path, or motion. And it depends upon what is your requirement. If your requirement is your output motion should be according to input motion, then it comes under function generation. If your requirement is a point on a coupler link should trace a specific path, then it will be a path generation. And if your requirement is a coupler link motion is important for you, then it will be a motion generation problem. I also briefed these 3 cases. I hope it is clear. Is it clear, these 3 cases? path, function, and motion. Hello.
So these all are problems, right? Synthesis
Uh,
problems.
yes, yes. Synthesis problem is some task is given to you, synthesis task. We need to classify that task. Means we should know which type of synthesis problem it is. Either it is path, function, or a motion generation. And according to what we classified this, I just told you. What Ashwin is saying, in analysis, we separate the components, while in synthesis, okay, okay. He's talking about analysis and synthesis. Okay. Yes, Aaron, any doubt, other doubt?
So talking about the function generation. So
Yes,
as we saw that output link is a function of input link, right?
yes.
So how can output link is a function of input link? How can it be a problem, sir?
Are actually
So
problem
it
means
is
it's a statement. It's a design statement to you. You have to design a mechanism. Listen, problem is what? A design a mechanism such a way that, let's say output link. Let's say talk about 4-bar mechanism. You have to design a mechanism such a way that your output link motion should be according to a input motion. So this design problem we call it as a problem of a function generation. Are you getting? It is not a problem for us. Means we need to solve. That
no.
statement comes under a function generation. Similarly, if you have to design a mechanism in such a way that, what is our requirement in that case? My requirement is a point on a coupler should give a specific path. Then I can call that statement as a path generation problem. And I solve accordingly. Now, how to solve this problem, that we see later on. Okay, but here just introduction to you means we need to classify the problem into three parts, basically a path, function, and motion. Whenever you are interested in output motion, then it is a function. Whenever you are interested in a point on a coupler, path of that point on a coupler, then it is a path. And if you are interested in a whole motion of a coupler link, then it comes under a motion generation. This is just theory part. Are you getting my point, Aaron?
So what I'm asking is, what is the problem, sir? Means the motions are a problem, or the point rest, or the path, or the links, the
You're
output
taking
link is moving this way.
problem word in another way. Problem means we are saying a statement. Are you getting what I'm saying? Problem statement, you can say. Problem is not a things to worry. Means we need to design. Problem is we say numerical, suppose. So we have to classify that numerical into 3 types. So we need to identify which type of numerical it is. Let's say. So I can classify that numerical into 3. 1, 2, 3. Let's say path, function, and motion. Are you getting? Problem is not a real problem. It's not a problem for us.
Yes, sir. Yes.
Okay.
Got it.
Okay. So any other? Are you getting these 3 types? Because theory question
Yes, sir.
can be asked in oral as well as in theory examination. So till now we discuss. First we discuss tasks, steps in synthesis. Now just we discuss tasks of synthesis. Okay. Now the last portion here that we have to discuss is after this. Yes, motion generation. One more example is there. You can see. Just go through this. Here, just go through that and tell me with what you understand from this. Can we call this problem as function generation problem? Sorry, motion generation. Means you should understand when we can call that a problem. Actually, I am calling problem means that you can say that motion is a part of that. Which task it is? Here, whenever remember, see here, whenever we are interested in motion of a coupler link, that's what. In this case, this third link, I hope it is visible to you. It is link number 1. Let's say link number 4 here, and link number 3 here. This one is link number 2, and this one is fixed link. So here the motion of this moving joints or link number 3 is important. When we are going to design a mechanism such a way that we are interested in motion of this link number 3. In that case, that statement, that problem we called as a classified as a motion generation problem. So this is one example. New roller blade brake system. This is just example point of view we just taken. Now next one. Now I talk about problems in synthesis or a classification of synthesis problems. That is path, function, motion. We talk about steps in synthesis. that is number synthesis. Which are the steps we discuss in synthesis problem? Synthesis. Which steps we discuss in the beginning only we discuss? Yes. First 1, 2, 3 we discuss it. And if you have to solve a synthesis statement, synthesis numerical, synthesis problem, we can say, then which steps you follow? First one is number synthesis.
Type, number, and dimension.
Yes, the first one is number synthesis, sorry, type synthesis. Second one is number synthesis, and third one is dimensional synthesis. So type synthesis means I just talk with you. Type means we need to select a mechanism. In number synthesis, we are going to select a number of links, number of joints, pairs, degree of freedom, all these cases. And third one, important one, we are going to finalize dimension. So here we are interested more in dimensional synthesis. In dimensional synthesis, basically we are dealing with determination of dimensions of links, angle between the links of the mechanism to satisfy the motion characteristics. I just already told you what is dimensional synthesis. In which we are going to finalize dimensions. It may be a number of length of the links, it may be angle between the links, or we can say distance between the links, like that. So here that is nothing but dimensional synthesis already known to you. But dimensional synthesis can be done in two ways, by two methods. One is by graphical method as well as by analytical methods. Means for dimensional synthesis, we have two options with us. We can do it by graphical method or by analytical methods. Now, which are the graphical methods? Which are the analytical method that we just discussed? That we will discuss. Now here, okay, we know that there are two methods, either graphical or analytical. Which graphical, which analytical, that we'll discuss later. Let's say, but the choice of method depends upon type of problem to be solved. So it is not essential that we should solve this problem by this way only. It depends upon which method will give you easiness. It may be sometimes graphical method is easier, sometimes analytical method is easier. It depends upon the problem. And one more thing here, the graphical method is an advantage that they are relatively fast in producing results, as well as it is easier to understand than analytical methods. That's why generally graphical methods are preferred in old age. But now with the help of computer, analytical methods are used widely for solving a synthesis problems. So analytical and graphical, both methods are there, both options are there with us. One thing I want to clear here, in your syllabus, that is your theory syllabus, Tom 2 theory syllabus, graphical methods are not there. I'm talking about theory syllabus. I mean, in your examination, theory examination, there will not be any question on graphical method. But in practical, out of there are total 10 practicals. Out of that, one practical is based on graphical method. Means anyhow, we need to learn graphical methods, but not in theory part, but in a practical sessions. And analytical methods we have to discuss in a theory sessions. So anyhow, we have to study both, that is analytical and graphical, but analytical in theory sessions and graphical in practical sessions. So dimensional synthesis problem can be solved by two methods, graphical and analytical. Graphical methods again are two types, inversion method and relative pole method. And analytical methods we'll discuss in detail in next sessions. For graphical, we have to discuss that in practicals. Now, before starting that analytical portion or method of analytical methods of dimensional synthesis, one part I have to discuss, which is important. 2-3 definitions are there, and then we'll stop. So there are two definitions I have to discuss here. One is what is precision point, or sometimes also called as accuracy points, and the second one is what is structural error. So I will try to define these two definitions with the help of this diagram. Now, let's say we have to design one mechanism, and that I am going to discuss with as a function generation problem. So we need to generate a function y, and that y is function of x. You know, x is input motion, and let's say y is a output motion. If it is a function generation problem, then these two types of graphs are achieved. You can see there are two graphs basically. This one is dark one, continuous line joined by continuous line. Another one is joined by dotted line. Now you can see here these two graphs are not matching, but there is some difference. You can see this. There is some space between these 2 points. So you can see here this one is difference here. So if I consider this graph at any point along y-axis, there is some difference between the 2 points on a graph at the same location of x. Let's say call that let's say talk about this point. So there is some gap between the graph, between the 2 points on a graph. You can take at any point. So there is some difference between these two graphs. Okay. We can say this dotted one represents a required path. Means I want y is equal to f of x. This is my required motion. But actually, when you are going to design a mechanism, that mechanism which is actually constructed, actually manufactured, will not give a results as that of this dotted one. But the graph obtained in actual case is one with a continuous lines. Means the graph obtained, the required path is this y is equal to f of x, but the actual path is not y. Actual path is not same, but it is satisfied this graph at some points. So there is deviation between required one and actual one. But you can see here at some points. Let's say at this point 1. Let's say P0, P1, P2, P3, and let's say up to Pn. At some points, both graphs are matching. Means our actual requirement and our requirement and our actual case, actual one is matching at some points. So we can see that is with these two. I think you understand what is our required function, what is our actual function, how these two graphs, what these two graphs representing. This one dotted one represents required path, and the continuous one represents actual path. So you can see in designing a mechanism to generate a particular function, it is usually impossible to accurately produce the function at more than few points. That's what I talk with you. This is our actual one, and this is our required one. You can see the actual one is not satisfying, is not matching at every instant, but it is matching at some instance. So our actual mechanism may give some error. It may be exact, it may be equal at some points, but not at all points. So there, it is not possible to construct a mechanism, or I'm saying it is not possible to generate a function which gives accurate result as the required one. So the points at which the generated and desired function agrees are known as a precision points. So I want to define these precision points. Precision points are that points at which generated function and desired function matches or it agrees. So that points are called as the precision points. So here P0, P1, P2, P3 up to Pn are called as the precision points. Remember here, precision points are those points at which generated and desired function agrees. Now we can see this point must be located so as to minimize the error. If there are more number of precision points, the difference is less. So both graphs are matching more closely. So in order to minimize the error, the precision point should be located at proper position. So it is very important to locate the precision points at proper position. You can see this point must be located so as to minimize the error generated between these 2 points. Now difference between the generated function produced by the synthesized linkage. Remember, generated function means the function which is produced by synthesized linkage, which is designed linkage. So difference between that synthesized linkage or generated function produced by synthesized linkage and required function is known as a structural error. So if I talk about this one, let's say here, this line represents structural error. So at this point, structural error is this much. Or at another point, there will be structural error. So difference between generated function and the required function is called as a structural error. This vertical lines represents structural error at that points. So I hope if you understand the difference between or the concept of structural error, definition of structural error, and definition of precision points, I want to ask you how much structural error is there at precision points?
0.
Good. Means you understand. So at a precision point, there is no difference between required function and the generated function. Both are matching, and hence structural error at these points will be 0. But at some other points, there is structural error. And if you need to minimize that error, then it is essential to locate these precision points properly. Now, how to locate these precision points? That we'll see next. Is it clear? Two definitions are clear. One is precision point, other one is structural error. Yes?
Yes, sir.
So what is precision point? Or we can say sometimes called as accuracy points, yes? What it is?
The points at which generated function and required function satisfies.
Good. Okay. And if there is difference between them, then it is called as a structural error.
Structural error.
Good. Now see, I told you it is very important to locate the precision points. So there are two methods basically used to locate the precision points. One is Chebyshev spacing method. Another one is overlay method. In some books, this shave, or you can say it is called as a CHEP also, Chebyshev. But the pronunciation, most of the people are doing it as a Chebyshev spacing method. Even though spelling is CHEBY, CHEB. Okay, whatever pronunciation it is, this is method developed by the scientists. Hence, we call it as a Chebyshev spacing method to locate precision points. This method we will not discuss as not in syllabus. So we'll discuss now this method and then we'll stop. So Chebyshev spacing method to locate a precision points. Last point. Actually, it is not something miracle. Just a formula is derived by this one, and that formula, that is this formula, xj derived by the Chebyshev, is called the Chebyshev spacing formula. So this formula is used to locate the precision points. So we can see the best spacing for precision points for the first trial is called the Chebyshev spacing, and it is derived by according to Fodase and Sendor, the Chebyshev spacing for n points. Remember, the points are n. We need to understand the terms here. For n points in the range of x varies from xs, that is starting point, to xf. Means if range is known to you for x, the number of points are n, then that number of precision points or precision position is given by xj, where xj is jth number of precision point. It may be 1, 2, 3, 4. Okay, so xj is equal to half of xs plus xf, where xs is starting point and xf is final point. This formula is already derived. There is no need to derive this. Xs plus xf half minus half of difference of them into cos of pi into 2j minus 1 upon 2n. The ready-made formula is there. Just we need to use this formula to locate precision points. In this formula, n is number of precision points, xs is starting point, xf is final point, or you can say this one is range. So range is nothing but delta x. So delta x is equal to final point minus starting point. So you can write here final formula as half of xs plus xf, addition of these two, minus this is nothing but difference, and difference is nothing but range. So it's nothing but delta x cos of 2j minus 1 upon n, where j is, let's say I'm talking about here xj, so it may be varying from 1 to n. So j varying from 1 to n, it may be x1, x2, x3. When I'm finding x1, it is this remains same, xs remains same, xf remains same. Only difference here, if j is equal to 1, we have to put here 1. So 2 into 1 minus n. If j is equal to 2, then it will be 2 here. So we can find x1, x2, x3 up to n point. So how many precision points we can find out depends upon how many precision points are given. It will be n number of precision points. So this formula is there. It is nothing but xj is equal to, that is jth number of precision point is equal to half of xs plus xf minus half of delta x into cos of this term. Means to find out precision points, what we must know delta x. What is delta x? Xf minus xs. So to know the precision point, we must know range of the x, that is xs, xf, and n. That is only sufficient to give you n number of precision points. We will take example on this later on. This is a Chebyshev spacing formula to locate precision points. Now, this is analytical formula. Graphically also we can construct precision points. So if how to obtain this by graphically means how we need to find out x1, x2, x3. Let's say you can see here range is given as delta x. If range is known to you delta x, that means if xf is given, xs is known, then we can find out delta x. So how to find out that intermediate points x1, x2, x3 by graphical method? You can see here. Suppose try to understand here. Xs is starting point, xf is final point, and we need to locate precision points. Let's say here it is x1. I need to find out how much x1 is, how much x2 is, and how much x3 is. So when range is given, delta x is known, xs is known, of course, and f also known. Then how to find this x1, x2, x3? That is precision points. We've seen by analytical one, we can use this formula. If xs is known, xf is known, then I can find out. And how many precision points we need to decide? Suppose there are 3 precision points, 1, 2, 3. So I can find out x1, x2, x3. If 3 precision points, x1, x2, x3 by this formula. This is one option with us. Another one is by graphical method. Now graphical is very easy. What to do here? First step, we need to find out range. And with that range, let's say delta x is equal to xf minus xs. With that range, we have to draw a circle. So draw a circle of diameter equal to delta x, first step. Then after drawing that circle, if there are n number of precision points, let's say suppose there are 3 precision points, then we have to inscribe a regular polygon having number of sides equal to twice number of precision points. So we need to fit a polygon inside that circle, and the number of sides of that polygon equal to twice n. So if n is equal to 3, then I can draw hexagon. So first step, draw a circle. Then inside that circle, fit a polygon equal to sides, and the sides is equal to twice n, where n is number of precision points. You can see here. So first we have to draw a circle, and you can see here diameter of the circle is equal to delta x, xf minus. So I draw in the first step, I draw a circle of diameter is equal to delta x. Then fit a polygon inside that circle, and the sides of polygon is equal to twice n. Here n is equal to 3, hence hexagon you can see. And the last step, once you complete hexagon, then through corners of hexagon. Now see, this one is these are the 1 corner, 2nd corner, 3rd, 4th, 5th, and 6th. Through that corners, we need to draw perpendicular. So I draw through this corner. Let's say 1, 2, 3, 4, 5, 6 are the corners. Through that corners, draw a perpendicular on x-axis. So I draw this perpendicular here. Next, draw perpendicular from this corner also. In this case, both corners are having one perpendicular only. So through these 6 corners, I draw perpendicular. Whenever this perpendicular intersect your x-axis, it gives you precision points. Let's say here x1, x2, and x3. This is your graphical method to locate a precision point. Is it clear? I repeat. First, draw a circle of diameter is equal to delta x. Second, locate a polygon having sides is equal to twice n. And third one, draw a perpendicular through these corners to get x1, x2, x3 up to xn. This is graphical one, and I also discuss formula to locate precision points. So in the last case, we discuss is analytical formula as well as graphical method to locate a precision point. Is it clear?
Yes, sir.
Okay. So I just repeat what we discussed in brief. Today we discuss what is synthesis of mechanism, then steps in synthesis, 3 steps: type, number, and dimensional synthesis. After that, discuss tasks of parameter synthesis. There are 3 tasks: function, path, and body guidance. After that, we talk about dimensional synthesis. And in dimensional synthesis, we discuss there are 2 methods, analytical as well as graphical. Here, before starting analytical methods, I just discuss with you two more important definitions, that is precision point and structural error. At the end, we discuss how to locate that precision points by using Chebyshev spacing method, by analytical formula, as well as by graphical method. This is what from today's lecture. Any doubt?
No,
Sir, the examples we saw, those are the applications where we need this formula, right?
Yes, yes.
Thank you.
Is any other doubt? Ashbin, in doubt is there?
Sir, one doubt. If there is there any possibility that we have only precision points?
What? Repeat, please.
Is there any possibility that we will have only precision points?
Only precision points. Hello?
Yes, sir.
Only precision points means?
Means minimal error or no structural error.
Yes, actually, now see, we can, but there may be some, that means we can say minute error will be there. But nowadays we can minimize the error with advanced methods. But we must know how to minimize the errors.
Yes, sir.
Okay. Now see, this is what about theory topic we discussed from unit number 5. Now next lecture onwards, we'll discuss numericals and derivation on this topic.